Welcome back, everybody, to our third video in chapter 12.1, where we're going to start doing calculus, finally. This is a calculus class. We've done a whole chapter, and now this one we haven't hit it yet because we just need to talk about three-dimensional space, two-dimensional space, how are we going to address it, and now we have functions, we're ready to start hitting some calculus ideas. But before we even get there, we're just going to say, hey, vector valued functions are functions. You can do a lot of the things you would normally be able to do. You can write down a sum of a function. We're going to call it r1 plus r2 is the name of a new function, and all it means is add each piece separately. So we're basically saying, hey, you can build new functions the same way that I can build new functions in a basic way. If I have f of x equals x squared and g of x equals x cubed back in single variable calculus or before, I can create the f plus g of x function, which is x squared plus x cubed. We're just doing that just with vectors. It just means when you're doing this addition, this is vector addition because r1 of t is a vector, r2 of t is a vector, so you can only do vector type things. But you can subtract the same way. You can do scalar multiplication. That's going to be like c times r1 of t is going to be c times f of t, c times g of t. It just multiplies the way scalar multiplication does, multiply every component. You can do a dot product that if I have r1 of t, I should stop being lazy, is f1 of t and g1 of t, and r2 of t is f2 of t, g2 of t, then r1 dot r2 is a new function of t. I want to take a moment before I write it down to point something out. Dot products take inputs that are vectors, but their outputs are numbers. So what is this whole function? You got an input that is t. You're going to compute r1 of t, that's a vector, r2 of t, that's a vector, and then you're going to do a dot product and get a number. This is weirdly written, but it is a calc 1 type function. Input is t, output is also a number, single variable function, which means you can do all the single variable things. You could ask what's its derivative and things like that. But at its core, this is going to be just f1 of t, f2 of t, plus g1 of t, g2 of t. It's just the dot product. Multiply your first components, multiply your second components, add them together. Cross product works the same way. As long as you're in 3 dimensions, you can do this as well. Cross product of two functions will still be a vector valued function because cross products give you vectors. Basically, you can build new functions from these building block ones. Fantastic, super exciting. I know you're all thrilled. Let's do some calculus. Let's do a limit of a vector valued function. Here's the thing. A vector valued function is kind of just sort of 3 functions all wrapped together in one set of brackets. And so when you're going to do a limit, you just say, hey, I'm going to do the limit of the vector valued function. It just means, hey, I'm going to do 3 limits. 1, 2, 3. It's 3 in this case because I'm in 3 dimensions. Provided all 3 exist. All 3 have to exist for this limit to exist. If even 1 doesn't exist, then the whole limit is t as your input approaches a single number. R of t does not exist. You need all 3 limits to exist. But otherwise, it's just single variable calculus, just, times 3. Or if you're in 7 dimensions, times 7. You take your limits. You have to be careful. You have to remember all those details from single variable calculus, right? Like if you have 0 over 0, that just means you got to roll up your sleeves and do some more work. If you get non-zero over 0, it's infinity. Direct substitution is your friend, things like that. But let's just compute one because they're really not that bad. We're going to do continuity first. In Calc 1, you learn that continuous means that 3 things are true. First of all, you learn that the function must exist. So you learn that r of a must exist. Now we're in multivariable calculus, so let me just add this caveat. It'll be a vector. because R is a function that takes a number, A, as an input and outputs a vector. R of A must exist. If it doesn't exist, it's not continuous there. 2. Limit. As you approach that number A, which technically means, because this is what limits do, t gets really, really close to A. You're plugging an input super close to the number A, and you're looking at the vectors and saying, are the vectors approaching something? Which is really just saying the points in space are getting close. Must exist. And then 3, these must be equal, which we often just abbreviate by saying, hey, R of A, if you're going to write it down, it had better exist. Limit, if you're going to write it down, it must exist. And if you're going to say they're equal, the only things that can be equal in mathematics are, I mean, we extend this a little bit, but vectors are allowed to be equal, but infinities are not. So it means both of these have to already exist, and then they're the same. It's the same as before. It's the same intuition as before. So let me jump way back to one of these things, that this is going to be continuous certainly everywhere except for possibly 0, depending on your definition, because there's no big jumps or breaks or anything like that. If your input is really, really close to 1, your output is really, really close to this dot. It's just that your input is sort of moving in time. So it's basically looking at the labels and saying, my labels are getting really close to 1. Where are we? And if you have a weird jump, like one is just way up here, but all the other ones are down there, then yeah, it's not continuous. But your intuition should be pretty straightforward. Let's compute a limit. Here we go. I want to compute the limit as t approaches 0 of r of t, 1 plus t cubed. I'm going to rewrite this one as t over e to the t. I'm going to leave this one as sine t over t. That's what we want to find. And so it's really 3 problems. It's really limit as t goes to 0 on my little scratch work here. 1 plus t cubed is 1 plus 0 cubed equals 1. Yay, we can take that first limit. We got a 1 there. And so tentatively, actually, we have 1 as the limit, because it just is do the first ones, provided they all exist. This second one, limit as t goes to 0 of t over e to the t. Now this one, there's division involved. That e to the negative t is really a division, so you may be a little bit concerned, but direct substitution is just 0 over e to the 0, which is 0 over 1, which is 0, which is a perfectly good number. I would argue it's one of the best numbers out there, 0. Fantastic. Now the third one. I'm going to switch colors because this one's a little bit weirder. Limit as t goes to 0 of sine of t over t. Direct substitution, just plugging in t equals 0. 0 over 0. What does that mean? It means roll up your sleeves, you got to try something else. A couple of ways you can do this. Number one is this is one of the core limits way at the beginning of Calc 1. It is the reason why the derivative of sine of t is cosine of t, is because of this limit. But you probably don't remember that. I remember it because I literally just taught it like 2 weeks ago. But you probably don't. And so what do? Well, one tool that we have is we have L'Hopital's rule. L'Hopital's rule, remember, is this lovely little rule that says, hey, you're trying to take a limit. You got an indeterminate quotient, 0 over 0 or infinity over infinity. Let's use derivatives to help us compute this limit. We're not going to do the quotient rule. L'Hopital's rule is not the quotient rule. We're not trying to find the derivative of sine of t over t. We're trying to find a limit. And L'Hopital's rule says this. You can take the derivative of the numerator. Derivative of sine of t is cosine t. You can take the derivative of the denominator. And if that limit exists, it's got the same answer as the first one. And this limit we can just do by direct substitution. This is cosine of 0 over 1, which equals 1. So L'Hopital's rule works out here. Make sure you're only using L'Hopital's rule when you have 0 over 0. At some point, we did have to work this out independently in some ways, because how do we know what the derivative of sine of t is? Well, the derivative of sine of t is a limit of, delta x, some such stuff. And the limit of the derivative of sine t is cosine t because this limit is 1. So in order to know the derivative of sine is cosine, you kind of need to already know this limit. But once you've done it once, now you're great. We get a 1. We're good. We do have a limit. Fantastic. How about the continuity? Well, it's not continuous at t equals 0. How do I know? Because there's a division by 0. It's not defined there. So it can't be continuous at that point. As a function, it can't be continuous. I could do some weird things that make the curve still look like a continuous thing. But as a function, it's not defined there. Everywhere else, it is. Because all of these other functions, 1 plus t cubed is just continuous everywhere. T e to the negative t is continuous everywhere. You're always going to be able to do direct substitution. You actually don't have to worry about the division by 0. Sine t over t, the only issue is t equals 0. All the building block functions, the x, y, z components, are continuous except at 0. And even at 0, we only have one problem, but 1 is enough. It is continuous everywhere else. Which is really to say that when we're talking about limits, it's kind of like Calc 1 times 3. If you're in 3 dimensions, only times 2, that you're just doing limits in the x, y, z. You just need to interpret your answer just a little bit differently, right? If 2 of them exist but the third one doesn't, overall limit doesn't exist. If you're talking about continuity, if 2 of them are continuous, our x and y are, but your z isn't, it's not continuous. That it's sort of like an all or nothing kind of thing. But otherwise, it's not that bad in some sense. Yet. That's it for this section, and I'll see you in 12.2.